Okay, so the next example that your book does, this is example 22-7, is an infinite plane of charge. Charge distributed uniformly with a surface charge density sigma, where sigma is the charge per unit area, over a very large but thin non-conducting flat plane surface. So we can consider the thickness of the plane to be essentially 0, and we can assume that very large means that if we're very close to it, we can treat it as an infinite plane of charge. Determine the electric field at points near the plane. So this is the drawing that your book has. The electric field we know goes outward from positive charges. We'll talk about the shape of the field in a minute. We can see the area they define. I'm actually going to set up the coordinate system a little bit differently than the book does. Let's create a three-dimensional coordinate system. Ooh, I don't want it yellow like that. That's crazy. Let's try that again. I want three-dimensional coordinate system. There we go. And so if we're talking about an infinite plane, it makes the most sense to just put that infinite plane in the xy plane in Cartesian coordinates. So we can consider a plane of charge, and we're going to position ourselves at some point P above that infinite plane of charge. What does symmetry tell us about the electric field here? Well, first of all, it tells us that the electric field will be in the z direction, right? If this is all positive charge, it's all going to push away. Any point over here in the plane pushing this way is going to be canceled out by any push this way. Any point here in the x-axis this way is going to be canceled out by a push that way. Any horizontal points on the xy plane are going to have their electric field canceled out by a point in the opposite axis. So we know that the electric field will be in the z direction. We also know that it can't depend on x and y because an infinite plane looks the same no matter how far you go in the x direction or how far you go in the y direction. So we know that at the very least the electric field will be some function of z, and it will have a direction in the z hat direction, the unit vector pointing vertically from that plane. The question is, what surface then can we use that has the appropriate symmetry to allow us to do our integral? So this sheet, and this isn't a great drawing. Let me see if I can... There, I cheated and paused the video for a second and drew a better charged plane for you guys. So we know the electric field is pointing this way. So we know that whatever surface we choose should be perpendicular to that so that we can easily calculate the flux through the surface. If you think about it, any shape we choose, as long as it has a face that is perpendicular to the electric field will be easy to calculate over that face. And if we put the same face down here, that's not a great rectangle, let me try that again. Then the electric field will be perpendicular to that face. And then the faces that connect those together, along those faces, E dot dA is going to be 0. Because the electric field is only in the z direction and the surface normals to these side surfaces are in the x and y direction. So we can choose a cylinder, we can choose a rectangle, we can choose an arbitrary shape for our Gaussian surface. It doesn't matter just so long as the top and bottom faces are parallel to the plane. We'll call the area of that shape just A. We could call the length and width x and y, but we'll see in a second we don't even need to do that. So what does Gauss's law tell us? Gauss's law tells us that the integral of the electric field over my closed surface, E dot dA, is equal to the charge enclosed by our surface divided by epsilon 0, the permittivity of free space. What is the charge enclosed by this box we just drew? Well, it's just the amount of charge that it cuts out of the plane there. And that's going to be equal to the surface charge density, which your book calls sigma, times the area, the cross-sectional area of our surface, whether it's a box or a crazy shape or a cylinder or whatever. So the charge contained within that surface is the surface charge density times the area divided by epsilon 0. The integral of E dot dA is 0 on the sides and equal just E times A on the surface. If we call the height of the box H, hopefully you can see that whatever the charge distribution is on the plane, the electric field is going to be the same on the top of the box and the bottom of the box, right? Because they're the same distance away from the plane. So we can just write this as twice the integral of E dot dA. And actually, we don't even need the dot product because we know that the electric field is perpendicular in there, over one of our areas A, right? The electric field dotted into the surface is going to be that way on the top, that way in the bottom. Those two things are going to be equal because the areas are equal and the electric fields are equal. So we can just multiply the whole thing by 2. That's going to be equal to sigma A over epsilon 0. And we already said the electric field can only depend on the distance from the plane, so it has to be constant everywhere on the top and bottom surface, which means that this is just 2E times the integral dA equals sigma A over epsilon naught. And again, there's nothing to integrate. The integral of dA over the area is just the area. And that's why we chose a shape that the electric field would be the same everywhere. So this is just E times A equals sigma A over epsilon naught. Okay. And again, because this A is non-physical, it doesn't represent any real piece of the system. It's just an arbitrary surface that we made up. It had better cancel out because it doesn't mean anything, and it does, leaving behind only, if we solve this for E, the electric field of this plane is equal to sigma, the charge density, over 2 epsilon 0. Notice, nowhere in this calculation did the height of our box enter into the question, which means that the electric field of this infinite plane does not depend on how far away you are from the plane. Whether you are close to the plane or far from the plane, the electric field is the same, constant. That may seem like a counterintuitive or surprising result. I'm not sure I can rationalize it to you right now and explain why that's the case, but if you think about an infinite plane looks the same no matter how far away you are from it. There's an infinite amount of charge in front of you. If you look all the way to the left, you see a charged plane. If you look all the way to the right, you see a charged plane. There's no difference from being close to an infinite plane and far from an infinite plane. So there's no reason that the electric field should depend in any important way on the distance. After you kind of process this and understand this example, take a look at your book and go through example 22-8. 22-8 looks at the electric field near a conducting plane, or even just one surface of a conductor. And what it finds is that the electric field near a conductor, if that conductor is infinite, is equal to just sigma over epsilon naught. It's equal to twice the result that we just got. And that's an important result because If you are very, very close to a conductor, it looks infinite, which means in the limit that you get very, very close to any conductor, the electric field of that conductor is just proportional to the surface charge density and doesn't depend on distance. This will become important again when we talk about capacitors. What's another way that we could see that this answer makes sense? Or another check we might have on this answer. If you remember a few videos ago, we found the electric field of a disk of radius, I don't remember what it was, A or R or something like that. If we take the radius of that disk and expand it to infinity, then the disk becomes an infinite plane and we should get that result again. Let's go ahead and stop this there. See if you can go back to chapter 21, find that result. I don't have it handy, but I know we did it. Yeah, it's over here somewhere. It's in my big stack of papers. Yeah, here it is. The electric field of a disk. Yeah, looks like this. We found that the electric field of a disk was given by sigma over 2 epsilon naught times 1 minus z over the square root of z squared plus r squared. And see if you can show that in the limit where r goes to infinity, this reduces to the answer we just got. I think you can probably see that that's the case already, right? It's really no big deal. If we look at this, what we've got out front here, okay, look at this term when r goes to infinity, this gets really, really big. This whole thing goes to 0. That just leaves behind the 1, and we get sigma over 2 epsilon naught. So one way to find the electric field of an infinite plane is to find the electric field of a disk and then just expand that disk out to infinity. And what we see is we get a result that agrees with the result we just got from using Gauss's law. So I'll go ahead and stop that there. And what we'll do next is we'll do one more example. I think we'll do the example of a charged sphere, and then we will think of what problems we could do for homework to explore Gauss's law a little bit further.